Hello folks, welcome to my YouTube channel. My name is Dr. Sudhamin Cap and today I am going to make my tutorial on class code. This is the first tutorial where I am going to show you how to install the class code as well as how to run a few programs and change something in the structure of class. I will also specifically show you in this video that if you have certain model, let's say the field model, how you can implement in the class code and you can run it. Today I'm not going to show you how you can also do MCMC with class code, but I will give you certain hints from which you can easily do MCMC. But the first goal of this series of lecture is how to fit your model in the class code. First of all, here is the home page of class code where you can read all many things about the class code, who has made it, right? And whenever you will use this class code, please cite those papers. They are incredible work, and also this whole software is extremely crucial in order to understand the dynamics of the universe, not only at the background level but also at the perturbation level. And you understand that solving the perturbation equation is not an easy task, and therefore by using just little bit modifications you can easily understand many things in cosmology, right? So first of all, the first question comes into our mind that okay, how we can download the class code. There is two ways to download the class code. First of all, you can just directly download the zip one. Otherwise, you can just go to their GitHub. GitHub is made like class public, and from here you can just simply go to code and download the zip button. Right. So if you are a user of if you're using the Windows or maybe Apple, the same thing take place. All right, just go and download the zip button, and then you have to unzip it and you have to place it in a certain folder, right? There is another way to download the class code or the CAM code, right, to use the to solve the perturbation equation. There is also another module called CAM, right? So first of all, go to Cobaya. Cobaya is a code where you can just do the MCMC. You can constrain the parameter with a whole set of data sets, right? So Cobaya is actually using the class. So you have a list of parameters you have to implement in the Cobaya, and Cobaya will call the class and try to give a constraint on those model parameters, right? So Cobaya is kind of framework where you have to first of all, I'm not going to talk about much in this video on the Cobaya. We will talk about the Cobaya in the later ones. First of all, we just have to go to the Cobaya, download it from just using download zip button. If you want to know much more about the Cobaya, here is a documentation of the Cobaya. You have to just go to the doc, all right, and just do the installation of the Cobaya. So the way to install the Cobaya is just using the conda or using the Python, right? So over here it is giving you that Python -m pip install Cobaya. If you have not first installed the Cobaya, you just use the code over here, and that's it. Now, if you have downloaded the Cobaya from this method, go to code and download zip button. What you have to just do, come over here and just use this particular code, Python -m pip install, then editable Cobaya or simply the Cobaya, right? How you have to do, you have to first place it in that directory. You have to open your terminal from that directory and then you have to run it, all right? Now make sure that if you are in Windows, then you have to open the WSL. WSL means for the Ubuntu terminal, and then you just hit it. Now one thing I am going to give you the thumb rule is that do not use the Windows terminal to run this code. Although Windows terminal is also very good, but you may get a lot of different type of errors. So best thing is either you are using the Windows or Ubuntu. Ubuntu is just incredible. Also in the Apple is also following the Ubuntu or Linux architecture, therefore it's also fine with this Apple. But if you are working with the Windows operating system, the best thing is that you have to use the Linux subsystem. Once you are inside the Linux subsystem, then you can do anything, whatever you want. So this is the way. Now in the Cobaya, you have many degrees of freedom. You can download many different data sets, because many people ask that where we can find the supernova data, where we can find different data sets. So what is the best thing you can do? Just you can see over here there is a cosmology section. In the cosmology section, there is installing cosmological codes. cosmological theory, codes and likelihood. So over here you can just use the cosmological theory, and over here what you have to just do after the installing the Cobaya, go over here, Cobaya install Cosmo. That's you have to first set the path, that where you want to install the different packages called camp and class. For instance, in my case, what in my case, I have unzipped my Cobaya in a Cobaya master, and inside you can see over here, inside the Cobaya master directory, you have Cobaya, and then I have placed everything in the code. So you can see my this directory is the D directory for my computer, right? So you can place anywhere you want. Although I am using the Windows, I am using the terminal, I am using the Linux subsystem. So I have already specified that where you have to install the camp, class, or different data sets, right? So let's say I want to use I want to download the Planck data set. So Cobaya install Planck 2018 high likelihood, high PLIC, TTTE, all the combination of the data, it will automatically download. So if you see over here, I have the data section, and the data section I have the 2018, right? So 2018 Planck 2018 and all these Planck. I have also data sets. For instance, I have supernova. In the supernova I have different data sets: CUVN 3, Pantheon plus, Pantheon, and JLA, DES, Y5, and DES topic, which is the recent one. So what you have to simply do is the Cobaya install, then these supernova or the SN, whatever you can name it, right? So in this way you can easily download the so over here you can just simply Cobaya install, and then I can write over here the class, right? So it will simply download your class code, also the Cosmo, also the entire Cosmo camp code, right? So you can also see over here the name of the codes, right? Inside I have Planck, I have class, I have many other things. So in the data I have Planck 2018, bicep 2018, and so on, right? So by using the Cobaya, I can download many different data sets. You don't have to look for anything. It's a very simplest way to download the class as well as the different data sets. Now how we can actually edit the class code, because I want to put my model in the class code, but first of all I need to understand how we can edit the class code. So first of all we have to go to the directory. I have this directory over here inside the Cobaya master. Inside the Cobaya master I have the code section. In the code section I have the classy. Although the name is class, but they have to name it classy because they are using the Python as a wrapper. Now since Cobaya is written in the Python, pure Python code, so class is configured with the internal structure of the Python. That's why they have named it classy. Now you have to go to the classy, and you can see many directories, and now you are you are in the C that okay, why so many directories, how we can even fit our model. That is again $1 billion question. So first of all what you have to do, okay, I need first of all edit my codes. The best way to do is that open the terminal by pressing shift and right click, and then you can see over here we have this open in terminal. Now once I have opened the terminal, I have to put WSL. If you don't know how to I install the Ubuntu in your Windows system, just to go and see some tutorial, or also you can see my VS Code tutorial. I have already shown you how to activate your WSL and install the Ubuntu subsystem, right? So it has already mounted my D, and there is a folder, it's called VS Code folder directory, and there inside a master, Cobaya master, and then go to code, and there is a classy. So this is also a way how to mount any kind of directory, right? Now once I have done is, if you just press hit ls, and then you can see many different directories and many folders, right? So these are different files, and in over here you have different other data sets or different folders, right? Okay, now another thing is I want to edit my code. So what you have to just do is write code and then press dot and then hit the button. Then you will see many download section, and here we are, our VS Code is downloaded and open. So since it is already downloaded and installed in my Ubuntu, then now it is directly opened. All right, so there you can see many folders will be shown in this arrow way, and when you press it, then this arrow will go drop down, and you can see many files, right? But before I'm going to tell you about the class code and how we can specify a model, first of all, we have to understand that the class code is written in C and some of the section is written on with the C++. Also, they have used the Python, right? You don't have to worry about those particular things right now over here. First of all, now we have to understand that, okay, if it is written in C, then how we are actually writing something in C. So I have made a very simple code to actually show you how we can write a code in C. Right, it's different from Python. Python is a higher level language, and the C is a very basic language which is actually directly communicating with CPU. And because since it is directly communicating with the CPU, it's called the low level language, and it is incredibly fast. You can do many things. If you use the for loop for thousand and millions, it can just give you in a blink of a millionth of seconds. Whereas if you just do the same operation in the Python, it will take a little bit time, right? Because since it is directly communicating with CPU, it is using a greater speed, whereas the Python is not. Python has many layers. That's why it is called a higher level language. So first of all, the way we are writing things in the Python, that we have to first say that, okay, import numpy or import certain libraries. Over here we have the header files. These are called the include, and dot is called .h is called header file. So studio is the standard library for input and output. And since my code says that, okay, ask the user to give the input and I will give you the output. Whatever the number whatever the number the user will put, I will just make it exponential. So I want the exponential of something in this code. So the way is that, okay, I am using the sine function, cosine function, or exponential function. The thing is, I need to use the mathematical header file. And there is, since I am using, I have to show the numbers, I have to ask the number from the user, I have to also specify that, okay, this is the return of something. I think that's a standard thing. I have to use the studio.h. So in any case, wherever you see the code of written in C, then these are the simple things. Studio.h will be there, right? Because it is going to handle all the important and trivial part of the C class. So first of all, I have to specify where is my main code, and it is the integer types, or people also can write void. Over here I have the integer int main and then parenthesis open and close, and inside that there is the curly bracket. In the curly bracket, now everything, the whole game is the code is executing. So first of all, I am asking from the user that give your input. Now input is the integer type, because exponential of ABC is, I don't know what is this, I can't know. So I have to tell my computer that, okay, whatever the user he or she is actually giving me the number, it has to be like integer type, but the size could be bigger. So and it could be also a decimal number. So use the double. Double has the large memory size, and it can accompany the whole number as well as the fraction number and so on. So I specify the double input. Now whatever the result, it is also in the integer format, so also make it double. So in Python, I can just write import numpy np.exponential of any number, and that's it, right? It will automatically choose that, okay, whatever you are going to give you, it will automatically decide that, okay, it is the float number or anything. But in the C, since it is a lower level language, it is talking to CPU, it does not know, right? So you have to first assign it what type of variable you have. So assignment is much more important. Now this is the same structure we are going to actually see inside the class code. So over here, printf that, okay, whatever the number you want to compute, just enter it, and then I have just use the if condition, that if scanf is it's asking the user that, okay, throw a number. If you have not given you any number, then I can just simply the invalid number, and then it will exit it, right? And if you have given the valid number, then it will just compute the exponential of input result, and then it will show that the result of exponential of this one is this one up to 4 decimal places, and then return 0, and that's it. This is the way, this is the the basic way to do programming in the C code. Now how we can run this program? First of all, you have to save it. I have saved it using the testcode.c. I'll just open my terminal over here. Now make sure when you just use the code, class code, you have already installed the C or C++ compiler. In order to do the C++ compiler, you must have the GCC, something called GNU-C compiler. All right. So either you have to download it in Ubuntu. I think in Linux computer it is already installed, but in WSL we have to install it. Then you have to write sudo apt install and GCC. It will automatically install the latest version of CSS. It will first ask a computer. I have already installed it. Now what we have to do, I can simply say GCC this is the test code .c. This is the now you have to do the output -o, and then I am going to write that I'll make an output like test code, and since I am using the mathematical thing, I'll just -ln. So once it is everything is fine, you don't see any kind of errors, and it will execute it. Now you will see I have the something called test code over here. It will not open, right? So it's kind of it is now built. Now I will do .s and then test code, right? Test code, that's it. And then I will press enter, and it will say enter the number you want to compute, exponential of something. Yeah, I want to compute 2365, and then it will tell me that it cannot compute because the result becomes infinity, because it's a very huge number, right? Again, I will just do, now I don't have to again rewrite the GCC. Once it is executed, we have already made this test code. Now since I am not changing anything inside the test code, I can use that same build, and I will just write /test code over here. I will write 26. That's it, right? So it means that exponential of bigger number is becoming very bigger. So now since we have used 1 2 3 4 5 digit number, it is telling me that it's giving me infinity. So how far we can compute? Let's see. Code, the number is 710. If you just press 710, it will give you infinity. But if you just use the 709, it will give you the whole number. So my integer, so this is the accuracy of this one. Now this is very important one, right? If you just use the scalar field, there are some places for some initial conditions you will have a very bigger numbers. So some parameters can diverge exponentially. You may have seen this kind of error coming in Mathematica when you will solve the scalar fields. Then it will simply give you the message that we run out of memory, or the number is huge. Then you have to control the thing that if something number becoming or exponential of, if it is bigger than this number, just make it lower and something, so on and so on, right? In the Python, you just have to use the clipping code, or you can simply write a simple code using the if statement, and everything would be done, right? Okay, leave it. I think it's a little bit out of whatever you can say. Well, back to our business. So this is the main thing. So where we can find the main thing? We can find the main thing over here. You can see there is a main, right? This is the main brain of this C component. So this is class.c. All right. So over here I have include class.h. Now you may ask that you have over here written class.h, but how does this computer know that people have written the class, have they already written this class.h? How my computer, how this whole thing actually knows that what is class.h? How it will read the header file? Yeah, that is a very beautiful question. But you can see this is the main file. Inside the class there is a int main, and it will have there is something called precision, there is something called background, there is something called thermodynamics, perturbation, Fourier, and all these things. It means that these are the things you can easily find out inside the whole class, and it is going to read those particular thing and give you everything. And here there is a statement, if input is such and such and so, then if it is not input such and so, give the failure. If it is there, then everything is correct, right? So it means that now we are understanding that there are so many things inside the class. Now where is stdio or math? How we can find it? Yes, now has include, I have now over here include button. Now I can see that there is a lot of things over here, class.h. So this class.h is coming from the include one. So now in the class they have defined a standard library. In the class now you have many things. Stdio.h, yes, standard library.h, math.h, there is string for string, things like float.h, which is for the numbers, openmp is for the parallelize, right? And then there are different modules. Now we have different modules, which is called quadrature, growth table, arrays, differential equation solver. There is parser, there is common.h, input, background.h, thermodynamics.h. So now there are different things, but now I have understood that okay, in the class.h all these have been included and they have made a separate file for standard libraries, right? So now you can see over here, since they have already specified that hashtag include background h, then I have to search where is my background.h over here. Yeah, now we are inside the header file of the background.h. Now this is the way actually reading the code. All right, now we can see that okay, in the background.h I have the few equations, right, that is actually coming to our mind. All right, so let me just actually show you that what are the equations. There is a first Friedman equation which is called 3h square is equal to kappa square. Kappa square is basically inverse of Planck mass. And then we have different row. Let us say rho radiation, rho baryon, rho cold dark matter, and rho lambda, or let us say rho dark energy. Inside the radiation we have ultra relativistic particles, relativistic particle, maybe there is some kind of neutrinos and different other species. Similarly, for cold dark matter, I can divide is a cold dark matter, also non cold dark matter, and so on. There are different configurations. Similarly, for dark energy, we can have the cosmological constant, right? We can have cosmological constant, maybe some fluid equations, maybe some variable dark energy, or maybe we have some scalar field. So there are different ways to handle it. Similarly, this is the first Friedman equation. We have the second Friedman equation, that is called Anisotropy equation, or 3s dot 2s dot plus 3 square is equal to minus kappa square. We have this P total, PR plus PB plus P cold plus P of dark energy. For cosmological constant, it is become -1. For cold dark matter, it is 0. For baryon, it is 0. For radiation, it is 1/3 of rho r, right? Now, another thing is that how we know that how these components are actually looking like. There is a simple way. There is the continuity equation, which is conservation of energy momentum tensor. Del mu mu nu is equal to 0, right? It's coming from the Bianchi identity. So what we are simply say that rho I dot plus 3h rho I plus P of I is equal to 0, and we have to understand that Pi is equal to sum omega I rho I. So I is for any component, right? Either you can just place with R and so on and so forth, right? So if I have the dark energy cosmological constant, this cosmological constant have the constant rho lambda, right? If we have this let us say CPL or CLP, right, where equation of the state has the particular form of omega 0 plus omega A 1 minus A, then we understand that this is the dynamical form of dark energy and there are different things, right? So using this equation, this is the differential equation that we need to solve. If I know, then I will get a function of rho in terms of A. Now I am telling you right now that whenever you want to invoke your equations, right, inside the class code, they are basically written in terms of d rho over dn. N is dn basically hdt or d log. If you will see my paper, I have written specifically it is dn, right? Because in dynamical equations we already consider our equation in terms of dn, because again we have normalized it, and we can once we have solved the equation with respect to rho by dn, then we can easily interpolate with respect to redshift z, because you have to understand A is equal to 1 over 1 plus z. So log of A becomes minus log of 1 plus z. So if I know the solution in terms of one variable, I can easily interpolate the solution with respect to redshift and so on. This is the standard thing which I also use in my own code. All right. So when I saw that they have done it incredibly, they have updated it in 2020, but this is the best way to actually do it, right? Because in many times we don't know what is the specific solution for this one, right? Now for the radiation case, in some case we know if you solve this differential equation, you will see that rho is equal to rho r, which is let's say rho r of A is equal to rho r of 0 a to the power minus 4. If I have the baryon case, I know baryon 0 a to the power minus 3, right? So this is the standard way to actually write the write the equation of this one. Once you know what is once you can easily solve this one, right? There are also interacting case where there are two components whose right hand side is not 0. So in the interacting case, what happens in interacting dark matter, interacting dark matter energy, rho dot, let us say this is the dark matter, 3h rho dm plus p dm is equal to, let's say there is something called q. And similarly, if I have dark energy, 3h rho dm plus pde is equal to minus, in such a way that this whole total equation will satisfy this equation, right? So if you see that individual components is equal to 0, it means that they are conserved independently. If it is not, then they are interacting and they are conserved together, right? So that the whole equation should not be changed. The total equation has to be remain conserved, indeed, right? So this is called the idea. There are different things that you have to understand. Now for certain cases, I know what is the solution. Now how we can write it, there is another way to write it, because these are the scale dependent, these are the scale dependent quantity. I have to make it in a scale independent quantity. How we can convert it into scale independent quantity? Let's say I have 3h square, right? The first Friedmann equation is equal to kappa square rho r. I know the solution, rho r 0 a to the power minus 4. Now I will simply divide it by 3h square over 3h0 square is equal to kappa square rho r0 over 3h0 square a to the power minus 4. Now they have defined this term is equal to e square. Now here this becomes actually rho r0, omega r0. So if you have seen so many papers, they have actually scaled it, rescaled it, normalized with respect to 3h square 0. So now you don't have to worry about the scaling quantity, but you have to worry about so everything is now dimensionless. Right, this is the basic way to do the dynamic system stability, but there is the same framework people are using to do the data analysis. So now we have this constant omega r0, and this is the constant we need to actually find out from the MCMC, from the data we have. Now in the class code is not for the MCMC. It is actually asking you there what is your omega r0, and I will try to actually, we have this power spectrum, and I will try to actually see that okay, is it matching or not, what kind of things are matching or not. So it is actually taking some input from the cosmological observation, and it tries to also predict what is your omega r0 and so on. So basically this is the framework. So you have to worry about omega r0 if you have the different let us say that you have a different dynamical dark energy. We have this omega 0 and omega a, and we have to always write it in terms of a, and you don't have to worry about it because the internal dynamics or internal code will automatically interpolate with respect to dn, right, or n. It will automatically interpolate with respect to the redshift. It will also interpolate with respect to something called eta conformal time. Conformal time is defined. It is now very important thing, conformal time, because you have to eventually do the perturbation, and we write the code, we write the metric in the perturbation like it is in the background. We always write it for the Friedmann equation like this. Now when we will bring out a square, it becomes a square plus dx square, right? So there is no a over here. Now this guy we call it, with this guy is called the conformal time, dx square, right? So now what we call, we have to do the integration to actually find out what is the eta, right? So this is the conformal time. Whenever we do the perturbation, we have to express everything in the conformal time. But now once you have described everything with respect to a, then the thing is actually it will automatically taking care, it will automatically take care of all these things, and you don't have to worry about it. You don't have to even worry about it. Okay, so this is the job actually. Now once I finish it, I have to worry about this guy, right? And this is the standard equation, rho dot plus 3h of rho I plus pi is equal to 0. This is the differential equation you have to solve in order to actually find out what is my Hubble. So now once I know what is my Hubble, I can easily find out what is my luminosity distance, because this is, I guess, c into 1 plus z, 0 to z, I guess, and this is dz over h of z. I may be wrong. You can just see there is the angular distance. You can easily derive it from dl over dA, sorry, dl over 1 plus z, and so on. There is also a co-moving distance of dh, right? So this is maybe c of 1 plus lg. There are a sort of different distances. Either you use for flat metric, or you can use for open or closed, whatever you want. Everything is already inbuilt. So the idea is that there could be many components inside the universe. For each and every component, you have to understand what is their role, right? What is their pressure, and in the class code you have to also define what is the pressure over dn. Right now, this is very important. Whenever you fit the model, you have to also supply that, okay, I have to, a is equal to log of a is n, right? N is equal to log of a. So you have to convert it into exponential of n and so on. So maybe you have to, give a dp over dA or dp over dn, correct? You have to supply it. Now, once you have supplied the information, then it is, everything is already accounted for. Now, why they have asking these two guys? Because now these are important, because they are also computing CS square, that is called sound speed, and also they are computing the RD, that is something called sound horizon. Now, sound horizon depends on the background density as well as the photon density, and also you have the Hubble parameter, right? So for those quantities, this is important, and there are several other quantities which is also coming under the background equations, because they do not want the perturbation, and simply called they can complete. So CH square is basically delta P over delta rho, and you can easily write it as dP over dN, d rho over dN, and that's why they actually want this CS square. Similarly, there is another something called adiabatic. So this is basically the adiabatic sound speed. That's why they need the perturbation derivatives, right? So this is the basically whole agenda of this thing. Now, if I see the background.h, what I can find? I can find that they have already including the common, the grow table, the arrays, and the RK4 solver, or different stiffness solver, and there is something called parser. Now I am seeing something. I'm seeing something, but where is this rho dot? I don't know. What is this rho dot? How we can find it? But I can just see the names, struct background. This is double. What is this? I don't understand. So then we have to again come over here, the source. Now we source, there is something called background.c, because here you can see it is everything is include.h, right? So here is written as background.h. Right, this is the header file. This is not an executable file. Where we can find executable file, we have to search where is this .c. So over here you can see there is a Python. Now in the C, in the source, you have written everything in C. Now because this is what we want, something.c. Now in the something.c, you have to read all these things, right? Then now it is actually incorporating hashtag background.h. Now you have to understand that in the background.h they have specified everything. Now what they have specified everything? They have specified, let me just tell you, they have what they have specified. They have specified the structure of the background. So let's say you have a book and you are actually want to go to some specific section, or you want to see the content of something. Then minded, this is a kind of a table of contents, right? Now we understand from these equations what we have. We have this rho r, we have this kappa, we have this h, right? We have this dn, and so on. As I told you that whatever your input, you have to first understand that the C program does not know what is this variable, or what is the type of this variable. So you have to very specify it. So over here, what they have done, they have made a dictionary of background, something called struct background, and in the parenthesis inside the curly bracket, they have initialize, or they have tell that, okay, these are my variables. Double h naught should be double, omega g, omega gamma, okay, photon density, temperature of CMP, that is called also in double, omega 0, this is the baryon density, also has to be double, right? Similarly, omega 0 DC over. So this is the dictionary they have already made. They do not want to clutter their main code with these kind of type of variables. So they have made everything inside the background.h. So in background.h, you have to remember that if you want to put your code, put your model, you have to also specify what is the what is the different type of variable you have used. So you can simply name it that okay, this is the double of that. We will come over here, right? Now background.c, this is the array 1. I don't need to care about over here. I just told you log a is what is this, minus log of 1 plus z, and then there is a test1, and this is the background of tau is basically the eta that I told you, right? And to now come to, yes, now over here we have this background function. Now in the background function there is something we have to write it. Now in our function, in our simple program, I have not written anything inside this one, right? But here I am writing it because I have a dictionary. I have made it in background.h, right? Now my job is I can take my stick and I'm telling that okay, you have to go this side, and this side. So that is the work is given by this structure, and that is the name that is called background. So instructing go to background.header. There is a background file we have made, and this is the pointer I have made, star.pba. Star.pba means that the pointer you have to point it out. Just like whenever you do the presentation, you take a pointer and you just specify that which thing you are talking about. This is the job of this PBA. So PBA, you can say whenever you will see here PBA, it is the pointer for background. Now double, I am specifying the scale factor A. Double, I am saying that this is the P vec B. Now you see that I can, because in our mathematical versions, we know what is this rho r. Rho r is basically function of thing. Rho r0 8 to the minus 4, but computer does not understand what is this function and so on. It just only understand the numbers, right? So P vec B is containing the kind of a tray. In the tray we have many different arrays. Just like imagine an Excel sheet. In the Excel sheet we have this A column, B column, C column. So this is P vec is something, let us say an Excel sheet where you can just go to different columns. In the different columns I can store my different arrays. So this P vec back is actually telling you that we are actually storing the different important parameters over here, arrays of this one. So now this is the B type of P vec B, right? This is not the initial thing. For instance, P vec is actually containing the arrays that are relevant for us. For instance, I am containing the density and so on. Now P vec B is different thing. Let us say something is integrating and I don't require it in the main function. For instance, I have a scalar field, right? I have a scalar field rho, and it's depending on phi dot square plus v of phi. Again, I have to convert it into array. So how phi dot square have certain array, v phi has certain array. So I will store those information of array in the P vec B. So again, it is also a pointer type of array, so that I can make it like there is a way why I have used also kind of pointer type of array. It's more like dynamical. Depending on the size, I do not want my P vec or I don't want my Excel sheet to be a constant type. I say that okay, I need this Excel sheet to have certain number of columns depending on the choice of the parameters we have. I don't say that I need thousands. Sometimes what happens is that it can increase or it may decrease. So we have to also, when I'm writing the code in C, I have to be very careful about the size of the arrays or size of the Excel sheet. I don't want to, we have to also do the memory management, because this code is going to be called not one time but many million of times. So if you do not do it intelligently, your system is going to store many chunks which is not useful for us, and the system will face many different challenges, right? So that's why we are using, whenever we have the array, we are using in such a way that it has to be dynamical. Similarly, I have a vector format which has certain informations and it will return certain format. So we have a enum for the numbers. Or you can say that okay, let me just show you what is this. I have a background.h, and you can see over here vector format. Now in the vector format I can store certain infos like short info, normal info and long info. That's why it is a list of certain names we can store it as a enum, right? So it has already given over here. That's why we are using the enum of and the written format. And similarly, again, I am using the density, H0 array, and all these things in the pvec. So there are different Excel sheets, you can understand. Now, for this background function, I need row total, because here there are certain quantities which are not, I'm not going to use everywhere. In the background.h, if I need, I will, if certain parameters which I require many number of time, then I can simply specify those particular quantity into background.h, because I am using those particular thing again and again. Over here, I am using the double row as total and row. It's a very local thing for this particular background equation. Now you have to understand that this integer background function, it is not int main, right? So we have made something similar to def, right? If it is in Python, we are writing def, let's say def this YouTube thing, and then we are specifying something, and then later on we are returning it, that return something, that this is the thing. So this is the same thing over here. We are specifying different blocks. So here is one block that is actually computing background function. It is computing row total, row critical, p total, row r, row m, and this is the known cold dark matter, and there is something called phi prime, and so on. Now we have to just, once we have given what is this double thing, we have to also initialize it, that okay, first of all make it 0, and then we are going to, because we are going to treat it as as a box where it is actually consuming all the numbers. First of all, as I told you that in my radiation have many different things, something, let us say photons, ultra radiation, and so on. So what it's actually telling that okay, make a row total, right? Row total, first it will have the information regarding rho g, because what is this? 3h square is equal to kappa square row total, right? So the program has been made in such a way that you can add many components. You don't have to worry about it. You can also discard that, okay, I don't need this much component. I don't this non-cold dark matter. So you don't have to come on over here and then you have to do this, you don't have to do the comment out, right? Sorry, you don't have to comment it out. What you can simply do, you can have certain things. Let's say I have just given that if PBA, pointer of background, has CDM, if it is true, then you can compute everything and put it inside the row total. If it does not have, then make it false, and we have this row total of photons and baryons. So you understand that photon and baryons would be always there, because again these are the essential component. But sometimes I want, because cold dark matter, I don't know about its nature. I can make it interacting cold dark matter, or I can make it non-cold dark matter. So it is in my hand, right? So you can, that's why we have placed, or they have placed inside the block, that if it is true by the user, then do this. If it is not, then leave it as it is, right? So that's why we have defined everything locally. Now, as I show you that I am using the density of what? Density of omega g with respect to what? A. So omega g constant, omega 0g, I have already specified PBA. Now omega 0g is inside the PBA. So I am telling the pointer of BA, go there, and because if I just remove this guy over here, it does not know, it will simply give you the error of omega g, because I don't know what is this. That's why I am saying my pointer that this is the pointer, and this information you can easily find out in the background.h. From there I have already specified that this is a double type, right? And then I have also specified h0 inside the background.h. So power of h0 square, this is the way to write it, h0 square, correct? And similarly a4. So what is this? I am using the background rho g. Now let me show you that how we are actually writing this one. So as I told you, this is the e square, right? Omega r0 a square. So e square is my h square over h0 square, omega r0 a to the power minus 4. So it will become h0 square is equal to h square is equal to h0 square, omega r0 a to the power minus 4, right? Similarly, I have basically what? Rho r is equal to rho r0 a to the power minus 4. I can multiply kappa r square over 3h0 square is equal to no, I can simply say this guy omega r0 is equal to kappa square rho r0 over 3h square. Come on, am I right? So I have this omega r0 3h square is equal to kappa rho r0. Sorry, rho r0 is already done, is kappa r square 8 power minus 4, that is rho r, right? So this guy is 0, this guy is 0. Now k can be easily made it constant, we don't require this kappa. So it simply tells us that okay, what is the rho r, because it will automatically multiply everything by kappa and so on. So what it simply says that okay, omega g0 power of h0 square, right? And just do this 8 over 4, and now this will become your rho bg. That's it. So rho r is your omega r0 h0 square a to the power minus 4. So I am just first of all defining my energy density of the photon. Similarly, it will have some certain array over here. Go back to this pvec excel sheet. From here I can again put that information in the row total, and then I can compute p total of 1 by 3 of row, dp total of that particular row, right? And this is the radiation. Now since this is the radiation, I have this photon and so on. So just use this particular array with rho r. Similarly, I have this array for omega p, omega 0 p, h square over a cube, p total is 0, therefore dp over d log a. Here is a log a, right? Which you have to derive for this thing. This one is p total is 0 and so on. Now if it has CDM is true, then just do the same thing over here. If it is interacting dark matter, then this is the thing. If it has the descending dark matter, then you just do this one, decaying dark matter. If it has the dark radiation, do this way. If it has the scalar field, then you have to do like this way. If it has non-cold dark matter, then we have to do certain things. If you have this cosmological constant, now it comes to the dark energy, then it is true, then just do the rho total is equal to the same thing, omega lambda, put it over here, p total is this one, dp over dn is equal to 0 and so on. Now over here, since lambda, everyone can do lambda, but what we need to do, we need to do the dynamical dark energy. Now suppose I have this dynamical dark energy where this wa and there is constant cs square, because whenever we have the dynamical dark energy, the sound square becomes negative. If sound square becomes negative, it means that it cannot execute anything, because it will return you the complex number, because it has been seen that the dark energy has the phantom type of thing where equation of a state becomes -1 to something. So whenever your equation of a state goes to lesser than negative, then the cs square becomes imaginary. That is the problem. So that's why over here what we actually do, we can just specify that sound square cs square is equal to 1. So over here if we have this lambda, then lambda we can simply over here for the fluid equation we have this constant cs square is equal to 1, and we have this wa is equation of a total equation of a state of the dark energy just from dark energy, right? Now it will actually have this rho. Now since if you have the complicated structure of the rho fluid, right, now we have to solve the continuity equation. So for now we don't know what is the actually solution of the rho, right? So it will go to pvec b, that okay, I am first of all solving this differential equation, and I will first store it in the pvec b. Pvec b is storing the b part of the the different excel sheet. Use the information from that particular excel sheet and put it in the over here rho bg. So pvec b is actually storing the information from the integration which we will solve later on, right? And then put it over here. Now how we can actually find out this omega fluid? There is another class which is actually made over here, the background w fluid. So class is calling that particular thing where it has certain structure, because if you just put it over here, you can simply see that int background w fluid, it has the structure background, because again whenever we make any kind of function, we have to struct it that okay, there is a struct background, because those are the information we need to use. There is a double a This is a double W fluid. Again, we are using certain kind of an array which is can be changed. Double of dW double dA, right? And then double of integral fluid. Again, we are doing some kind of integration and also using that particular integration over here. So you have to use the same structure over here whenever you can call it. So struct background, so I am using specifying BBA, right? Similarly, I have this scale factor A. Now, since I have already specified W fluid as a pointer or the dynamical kind of array, so W fluid, I am just storing the address of W fluid. So once you know the address of certain array, you can easily find out what is the value of that particular thing. So we are storing the address. Similarly, dW over dA, again AND is denoting the address, and similarly address for integral fluid. And then there is a PBA error message. If there is an error message, then it does not know what is the error message. You have to pointer it to error message. You have to pointer it again to error message. Now, from that particular thing, go to pointer index of BW fluid, and from there you can easily find out what is your W fluid. W fluid is this integration, and pvec is the Excel sheet where we are actually having certain kind of index, certain kind of column where it is actually storing the array corresponding to the equation of the state of that particular fluid, right? So here you don't need to change anything. Now, once you know what is the W fluid, I can use that, okay, row total is the pvac of this row index B0, right? P total is the W fluid times that particular array over here, W fluid into row, right? Because P is equal to omega into the row. So over here I have this row information from here, just put it over here, and then dp over dn I can easily put over here, right? For any kind of fluid, this is the general result, right, for any fluid. So wherever you will have certain things, you can easily put it over here. So you can easily see, let's say P is equal to W, which is also depending on N, and rho also is depending on N. dp over dn becomes dw over dn times rho plus w into d rho over dn. Now, what is this d rho over dn? We have this rho dot plus 3h rho plus p. I can write over here 1 plus w into rho is equal to 0. Now, d rho over, I can just divide it by h dt is equal to minus 3 into 1 plus w into rho is equal to 0, right? So this is now becoming dn minus 3 into 1 plus rho into this one. So this is corresponding to W fluid, right? Now you have to put it over here and you can easily get dp over dn. So this is the way we can easily get a dp over dn, right? Once we are done with this thing, this guy is finished. Here there is ultra-relativistic neutrinos or dark radiation or anything. It is not our use. Now here it is storing our H. It's actually giving you see over here kappa and A square, right? So squared rho, and it is also having a square doing this PVA minus K. So this is for the curvature one. Let's say if you have this flat curvature, K becomes 0. If you do not have curvature, if you have open, it becomes 1 minus 1 or close for plus 1 and so on so forth. So it is actually making an array for H. It is also making an array for H prime. There is total energy density. It is again storing it inside the big total, inside the BG total. So first of all, it has taken all the information and now putting it over here. So that's why it has not first made an array. In the end, we have to make an array in the Excel sheet of pvec, right? But once you know all the information, that because not all the information is containing inside the row total, there are few information we require. So once we know, we have already clubbed together all the information. Now I am going to use that to put it in the Excel sheet. Similarly, dp over d total, dp over dn, or everything is over here, right? I can compute the rho critical. Also, I am going to make input it inside the pvec of omega r and so on. Now here this is not of your use. Once it is done, we will talk about this one later on. And here we have written success. If there is any kind of error, it will automatically show that there is something error in this block and so on. Now, since we are interested to put our fluid over here, one thing we for sure for know that okay, we have to go to background W fluid. So either I have to click it just in the VS Code, just you can click it, control plus click, and you can easily directly go back to W fluid. Again, W fluid, we have made the structure, the same structure. Now what we want W fluid dw over dn, because that is important, and integral of that particular fluid. Now I have to, there is again early dark energy they have already introduced. So in the fluid equation, there could be many fluid. For instance, there is a logarithmic kind of fluid, there is different other kind of fluid. Let's say I have this bell type of fluid. In my paper, I have we have studied something called the Gaussian nature of dark energy, where I have specifically showed that the dark energy should be only become phantom just at this, at the current redshift or at the late time redshift. It should not be all time phantom in all the redshift. And if you just use this particular model by using the evidence of the model, we have found that this model is no difference from the CPL model. In the CPL model, you see that all the time it at the high redshift it requires to be phantom, right? So we have shown that it does not require to be phantom. If you use this particular model, you will have no difference at all. So that's how it is also solving us problem that okay, we have to solve the problem in a more specific way. We have to if you want to investigate the nature of dark energy, then we can put our whole task in the present case, or in the late time, or in the lower redshift, not at the higher redshift, right? Now if for that thing I have used this particular dark energy model WDE of Z with respect to redshift W1 plus W0 W1, exponential of this kind of thing. So Gaussian type of nature. There is a delta is actually controlling the spread of this thing, and this is Z is the Z, and ZT is the transition redshift. It is again a constant, or you can use it find it value from the MCMC, right? Now you see we have this free parameters W1 W0 W1. This is delta, this is ZT, and Z I can easily convert it in terms of scale factor A, correct? Two things they have already invoked, that if you have the CLP model or CPL model or CLP model, then how you can find W fluid? Star W fluid, because we have already given that okay, this has to be dynamical. So star W fluid is equal to PBA. So inside the pointer you have the information of W0 fluid, W0 and WA of fluid, and 1 times A. So if you have this fluid equation, and in the fluid equation we have this CLP, I can actually find out CLP. Similarly, I have also said that okay, I need to also put my Bell model. Then what I can simply do that okay, go over here, compute. Okay, just I have put over here in case that okay, this thing becomes very large and so on. Exponential can be large, because but it cannot be large, because we have computing everything inside of negative of something. Therefore, there is no use of this particular function. But never mind. So dash star W fluid is equal to WA fluid, W0 minus WA exponential of UU. So UU is over here. Now I have specified that okay, you can also find this Bell ZT, because it's again a free parameter, PBA Bell ZT. Also I have put over here PBA Bell delta. Now this thing I have to use many times. That's why I have initialized it, or I have tell that my computer or my code that you will find it inside the PBA dictionary, right? So now it is computing star W fluid. Now we have to also study, now they have the case that okay, if there is early dark energy, so this is where you have to actually put your model like this, correct? Now once you have put your model over here, you have to again come over here. This is again break, again it is starting. You can also write it dw over dn over here, because this is the structure, dw over d over. But for the continuity, the way they have actually written, I have also using the same trick, dw over dA fluid, because the CLP model you can easily find out what is this. So it will simply become w minus of WA fluid. They have written like this, but in my case I have to compute specifically that what is the function of this one. Then I have dw over dA fluid. I have used my expression over here. Now I can break it. Now another thing, they have used the integral of fluid. So what they are integrating? They are integrating the right hand side of the equation, continuity equation. So let's say I have rho dot is equal to minus 3h into 1 plus w into rho, right? So they have put rho in the left hand side, rho dot over rho is equal to minus 3 into 1 plus w, right? And h, so this is h is basically a dot over a, right? So let me again rewrite it. D rho over dt times rho is equal to minus 3 into 1 plus w dA over dt times a. This dt cancel. So you have this now d rho over rho, simple integral, minus 3 into 1 plus w dA over a, or d of log a. So here you are actually integrating from a0 to a1. Since it is negative, so you can just make it positive. You may say that, okay, this is the a initial. A initial means that for any a, and here you have integrating to a is equal to a naught. A naught is basically 1 at our present case, right? So this is where a is any a and a0 is present. You have to integrate with respect to a, and this is the thing. If you integrate it, then what you will find? You will find this rho of log of rho is equal to this one, something like this. So you have to just find out what is the integral of this guy. Now in the CLP case, finding integral is very easy, but in my case integral is not easy. We have to do it numerically. That's why what we have told is integral of fluid is equal to 0. Now once it will read the integral of fluid is 0, it has already tell us that, you know, if your W of A does not lead to a simple analytical solution of this integral, no worry. Instead of writing something here, the best thing would be leave it equal to 0, and then in the background initial condition, you should implement a numerical calculation for integral only for A is equal to A9. Means that I need to find the initial condition. What is the energy density of this particular fluid at I at very initial time. Now A in E here is corresponding to 10 to the power minus 14, which is near about minus 24. If I just change it in terms of n becomes minus 20 or something like that, right? Or z becomes 10 to the power 14, something like that, right? So it is basically telling you that, okay, you don't know what is the energy density at the early time, just leave it here, integral is equal to 0, and there is, you have to understand where is the background initial condition. So I will just copy it, and then I will make the control F and just put it over here, background initial condition, and hit it, right? Oh, now we have come to background initial condition. Let me just go over here, background.c. Oh, we have another thing. Yes. Background initial condition. So they have already called background initial condition. I will just simply press click and cut over. Yes, over here they have made int initialize background initial condition. We have the structure that is called precision structure background PVA. So there is another structure called precision. So you have already seen some inside the include there is a precision dot h, right? Where is this precision dot h? Now inside the precision dot h, you will see that they have made various things. Now what they have made, basically they have made inside the precision A ini over default. So they have already specified the value of A initial, which is A 10 to the minus 14 in this one. They have not cluttered everything. They have systematically given you that where you can easily put it over here, where you can find something. Similarly, background of n log A. N log A simply it will take, and it can, you know, generate 40,000 points and so on. So whatever, whenever you want to use, change something, or you want to see that what is the value of certain quantities, you have to go precision.h, right? Okay, let's come back over here. So struct precision ppr. So this is the precision.h. I have to also come here precision.c. Where is this precision.c? Let me just, yes. So common dot. So this structure inside the Excel sheet or the dictionary for precision, you can find it in the common dot h. So when you just go to struct precision, they have already made it, right? They have made certain different things like double smallest allowed variation, what is the characteristic of base path. But I told you that they have made everything inside the precision dot h, that what could be the different values. So if you want to find out what is the A initial and so on, you have to just write PPR, and then you have to tell your pointer that go and take that particular value. So p vec integration, whenever we do the integration, I am going to use that particular Excel sheet for integration to store integration thing, and then I will use the p vec b, and then I will use the p vec a, right, or p vec, double p vec, directly using the best arrays what is required for us, and double log a in e, correct. So all the scale factor and so on. So over here, let's bring the a at any time, which is a initial over a initial over a today. So this is a initial over a0. So this is a over a0 by default, right? So this is the default where you can find it inside the PPR. I told you it is 10 to the minus 14. Now I don't have non-CDM. I don't worry about this guy. If omega radiation, then PBA omega 0. Inside the omega 0, you have this PBA. You can read it and you can easily find out what is the initial condition at particular time of thing, right? Now what is my case? My case is PBA when we have the fluid case, when we have the dynamical dark energy. Now for that particular case, what I'm going to do, I can find out what is the rho fluid today, omega 0 fluid, and this guy, right? Omega 0 fluid times this one. Now this is for any fluid, right? I can simply omega 0 h0 square, and this is just only for today. If you have any fluid, as I told you, that A becomes 1, there is no need to worry about it, just h0 square, and you will find out what is the corresponding fluid density at today, right? Now let's say I have a CPL, right? If you just come, I have already computed for my bell. Let me just tell you that let's say if you have, when you will use your class code, then you will find out that okay, class this background W fluid, because in the background W fluid I have already find out this integral, whatever the integral of that particular fluid, right? So I have already given the integral. So from the background W fluid, call the integral fluid. Here we have the p vec integration. It will just store the integration value. So rho fluid today, you have to multiply it by using exponential of integral fluid. As I told you that this will become log of rho times right hand side. So rho becomes exponential of this guy, negative of something. It will simply give you the initial density of that particular fluid at that time. Now over here, what I am actually doing, I am using the same trick for the bell. So if fluid equation is equal to bell, then I am again using certain things. Let's inside I have used wait a second, yeah, inside this structure, because I can I can have multiple things. I have CPL, I have bell, I have logarithmic of something. So here I am writing everything inside the if condition. So let us say I have another struct, something we have made generic integrator workspace as a GI. Now I'm actually defining start, right? Why start something 1D array, right? I'm not using, because it's again whatever the differential equation we need to solve, it's just only one differential equation, right? It is a very simple one. It's a one differential equation. So log a start is equal to 0, because log a becomes 0. Log a end becomes log a ini, right? So whatever the initial condition of a, and I'm using this integral with respect to n, not with respect to a. So EPS I can make for integration. I have to use the precision, and I have also defined the minimum step what you have need to take. At lower it can go, right? So now I am using the another definition, another structure over here, bell rho derivative, double of log a, double of y star, double of dy, and void something if you have any parameter, and then error messages or something. Now I am using again a structure. I can use it because I have already used the void of parameters. Then I am specifying that where you can find the parameters and so on using structure. Double of a is already defined, but still I am defining it inside the bell row and so on. Similarly, uu is the exponent of this something. I am using the exponential of uu, right? And this is the equation of state for the bell. Now once it is using, I am setting up that dy. This is dy over dn. of 0, right? This is the index of this equation, minus 3 into 1 plus w into y of 0, right? So this is dy over dn, and this is y of 0. So once, now this is the differential equation to compute the density at the initial time. Once it is success, I have to initialize first whatever there is a lot of integral they have made. For instance, they have made, there is a tools. In the tool, they have the RK4 and Range Gupta, there is ND15 for step solver, and there is another evolver RK and so on, right? So there are a lot of tools they have already made. You can directly also use these particular tools in your own code. Okay, so first I have initialized it, right? So y start, I have already given that omega 0 into PV0 h square. This is the y start, and corresponding to this, it will simply compute that, okay, whenever you have generic integrator, because again you see that you have to first provide what is your y0, y of 0, because again it is just doing the back integration from present to the past. So I have set up a local integrator, go from log a start to log a end. Y start I have already provided what is the y start, right? Because if you see the structure of, okay, whenever you have to, how do I know that I have to make it like this way? I will tell you in the next time. But if you just see the generic integrator, you see when I have generic integrator, it has tell us an integral of certain things has the format of double of x, double of star y, double of star y prime. So they have already tell you that, okay, if you want to do the integration, you have to very specific how you are defining your differential equation inside certain function, right? That certain function should be in type, and inside it, first of all, you have to find it that scale factor or whatever, double of x, double of y, because it's again an array, y prime, right? And then there is a void parameter, and then there is a error message, right? And then you have to, inside the generic integrator, you have to first define the x1 like initial condition, where from initial lower limit to higher limit. Then you have to also put that what is your double y start, what is the y start, where it should take a value, and then there is a void for another pointer, and then you have to define that what is the precision you want, right? And then structure of this particular thing, that what is the structure of this thing. That's why we have defined gi. So log a start, log a any, y start, pba for the parameter, right? Void parameter space, that you can just use the parameter from there as minimum, and gi, because it does not know. How does this generic integrator will know that what is your w0, right? It will not understand what is the pba. So you have to, I have told you that pba is a pointer. That's why we have passed over here. Bell row derivative has this certain structure like this, and we have already used this pba and so on. So once this is done, I will get p back integration index bi row fluid is equal to y of start. That's it. It will just give you one value, because I am doing the integral from a0 to a sum a, just one particular value. And then I will have to free up the memory and clean up generic integrator. This pointer I have cleaned up. So this is the same structure which we have found out for the CPL. So for CPL I have used else something, right? Then there is an exponential of something. For us, we don't require exponential of something, it will automatically compute everything. Or we may also do the exponential of something, but yeah, that's it. All right. So this is the interesting way to actually get it. Now, since why we are not doing the initial condition, because here we have d row over row, we are not just doing d row over row, we have already multiplied of y0. That's why we are not required to actually multiplying with exponential, right? If you do the exponential, you will get the wrong result. Now, since they are just solving the right hand integral, that's why we are solving the differential equation, and we have put the information, passed the information to p back integration, right? So once these are two things that is done, then you are good to go. You don't have to do anything else over here. If you want to see how it is solving, you have to go to background solve. So if I write over here background solve, now in the background solve, they are actually solving everything. yeah, in the background. So they have a structure, precision and background, and inside the background they have already made the structure background workspace as a ppw. They have again forming a local structure for ppw, so that they can just the way I have followed, that I have made a gi, right, made a workspace. So for that they have set up everything inside the class, and inside the class they are actually using the rk as well as nd15, but every time they are actually using the nd15. I will let you know different time. Here they have used, this is called generic evolver. Inside a generic evolver, again the background derivative, they are now using log initial. Log initial means that they are using a to a minus 14 to today, that is a1. Now you have to understand that as long as you are at the background level, you can do the integration from present to the past, there is no problem, since you are also using the fluid equations, or maybe you can use the scalar field equation. Going from present to past does not have any kind of problem. You won't get so many stiffness if your initial conditions are correct, right? I have also discussed it in my current paper. If you look at my current paper over here in the, this is the fermionic, yeah, interacting scalar field, dark energy, dark matter, Einstein Gauss Bennett case. I have actually shown that either you plant your initial condition at the past at the deep radiation won't give you another result if you just put the initial condition at the present level, right? Now there are many advantages if you put the initial condition at the present level, otherwise you don't have to do the mapping things or matching kind of things, right? Over here they are doing some matching things, that okay, if I choose some random initial conditions, here they are actually intelligently find the initial condition at the past, and from that past information obviously they will get the correct result. But in the scalar field you have to choose by some guessing thing, that okay, what could be the scale factor corresponding to dark energy and so on, and then they are trying to match it. It will consume a lot of cpu power, right? Now since we do not have much cpu power, you can also use the same strategy but plant your initial condition at the present time. I will discuss it more in detail, but over here now the question is that as in my case I have defined the pba zt. How does this guy know that, how does this c code will know that okay, where is this, how it will understand that okay, what is the bell? You have already given you the name bell, before it was just only cpl. So then we have to go to the background.h. Now in background.h you will first see that equation of state. Now equation of state you will not see, you will only see clp and ede. I have specified bell, that if in the equation of state there is a bell, then use those particular information, equation of state. Over here in the background, if you just go over here, I have also, you see all this initialize the int of index and all these things, has lambda, has thing. You can use also the same thing, has if you have different thing, then you can also say that okay, has another fluid and so on and so forth, but you don't have to do those particular thing. Now w0, I can search for w0 fluid. So right over here w0. So over here there is a enum equation of state which is called fluid equation of state. As I told you that if fluid equation of state has bell, so this is inside the enum, and then there is a double w0 fluid, double wf fluid, double cs square, right? And now I have also said that okay, double bell delta, double zt, because in my also model there is a w0 wa, so I have just used that particular name of that w0 w fluid. It does not matter that which one you have used. I have already specified that once you use the bell, then you have to use the w0 fluid, wa fluid. Also you have to use bell delta and bell gt. Now once I have done this one, how does the question comes that okay, how does this whole guy will understand, how does the main function will understand that these are my parameters? Then for that thing you have to go to common.h, not now input.h, because this input has all these things. So I am going to use w0. So over here w0, do you have w0? No, we have bell input dot, oh wait, in this, no, in this thing you are not finding anything, input dot c. sorry, so source, and we have input.c. Input.c, we have this bell. Now if you just type it CPL or CLP, you will find that in the input, first of all, the class has to know that which are the models you want to specify. So there is something called flag true. If there is a string, either you put CLP in capital or CLP, then the fluid equation of state will become CLP. Else there is a early dark energy. Now I have also used that. Okay, else if I have the bell and there is a bell, then I have this equation of state that is called bell. Right? Now if you have this CLP, then these are the equation of state you need to read for CLP. If I have bell equation of state, then these are the equation of state the class will. So these are the free parameters the class will read. W0 fluid, WA fluid, CS square, bell delta, and bell JT. So this is how we have told the class that these are under the bell, right? Similarly, EDA have this number of free parameters, right? Now there are something called the default thing, right? So these are the, again, similar thing. You have to go through all these things because they have also included a perturbation. That's why this looks so nasty. I have to use default. So if I go to default thing, now here I have the input default parameter. Suppose that you have, there is a default way, There are so many people who does not know anything. They will just simply run it. Then class, they do not want, they do not want to make you feel stupid, right? So that's why they have already defined something default, that by default these are the values of something, right? So they have already said that by default everything is false. By default a scalar field is some vectors true or some scalars are true, right? Over here they have already told that had scalars. If you do the perturbation, run the perturbation, it will simply run the perturbation, and it will simply run the perturbation for scalars. There are we have splitted the background equation into three different types. Scalar will talk to scalars, vectors will talk to vectors, and tensors will talk to tensors. So if you use the cosmology, obviously what is important is the scalar perturbation. So that's why they have by default made it scalars equal to. If you don't know anything about it, you just want to hit the class code, then they by default they have selected true, right? Similarly, by default I have also specified my own values. For instance, for the baron density, they have already specified what is the baron density, ultra relativistic density, and so on, omega 0, omega lambda CDM density. Similarly, they have specified the what is temperature and so on. Omega k, by default they have already given you everything. Now I have to find out if my equation of state is fluid equation of CLP, then omega 0 minus 1, CS square is equal to 1, omega A fluid is equal to 0, right? If I have the bell case, then fluid equation is equal to bell, W0 fluid is minus 0.98, CS square is equal to 1, WA fluid, let's say it becomes minus 1.54, bell JD 2.4, bell delta 0.95. So if you don't know anything, I have already specified over here, then you will just simply hit it and run it. It will not give you error, it will just give you this particular value. And if you don't know where to change, then it will keep on giving you the same result again and again, right? Now everything is over. What is the next thing? How we can actually run this program? Well, in order to run it, when you have put everything, what you have to do, you have to just open your, again, this terminal, beautiful terminal. You have to write make clean. But wait a second, I have implemented over here, right? And I just make clean whatever initial they have made it, I just make it clean. And now I have to use make -g. Now it will build you the file that is actually converted every English into the executable code, which is in the binary and so on, right? So all these things will become a binary code, and we will have that certain particular type of make.c, right? Now once we have converted this into the binary code, it will compute, it will say that okay, we have reinstalled the class. This is the way to reinstall the class. Now what we have to do, we have to come here, and there is a called ini file. I have made my own ini file, but you can use the explanatory. There is a two ini file. By default, there is a default ini file. You can use this one, and there is a explanatory ini file. Here they have explained everything. So you can just use the explanatory file. You can see that out in the output you have to use this particular data sets. There is a scalar that which perturbation you want to use, the mod s, right, for scalars, vectors and 2. So over here you can may use vector or tensor or anything, or you can just use svt the way they have used the scalar and tensors. Which kind of perturbation you have, adiabatic perturbation or non-adiabatic perturbation, you can use over here. Tensor method or gauge, we were by default it is a synchronous gauge. I can use also Newtonian gauge, right? H, in the H is basically H0 over 100, so you can just use 0.69 or 0.67, so whatever you want, right? Do not do anything over here. These are thermodynamic parameters. You can also change if you want to specifically make your model to thermodynamic perturbation, then obviously you will change these kind of things. TCMB, omega b is a baryon density. I don't want to change. I can change the ultra relativistic thing. 3 is equal to 3.044. If you just use this one, then all the radiation will become ultra relativistic thing. Okay, you can also include 2.044, then rest will be automatically accommodated accordingly. There is a omega CDM. Let's say we have, you can change it, or we can use the same thing, right? Now where we can actually find it, where we can put our own model. If you just go over here below, then you will see that here is a dark energy section in 8, in 6 or 6 9. So if you just specify nothing, then it will automatically by default it will understand that okay, there is a cosmological constant. If you say that okay, omega fluid is equal to 0.7 and omega lambda is equal to 0, then there is no any lambda. So omega fluid is equal to 0.7 and omega scalar field is equal to 7, because I need my specific thing. I need my specific model to work. And now since my model can go to the phantom line, therefore it will give me the error. Hence I am using the use PPF. This is the post metric formulation to use to give you the to handle the perturbation when you have the phantom model. If you want to understand what is the PPF, then there is a paper you can see over here, and you can understand that how it is how the post metric formulation or post perturbation formulation will actually can handle the approximation smoothly. And in that case you have to use C gamma over C fluid as 0.4. You can also, it's a default thing, you can just leave it. Now fluid equation, which equation I want to use? If you have the class code, you will see that there is CLP. So once you specify CLP, you have to also specify what is a W0 fluid, WF fluid. Now I want to specify my fluid equation as a Bell. I have to define what is my Bell GT and what is my Bell delta. That's it. That's done. Now in the output file, what you can simply see, if you just come below, completely below, then you can see that okay, I want to write the background quantity. That is over yes. I don't want to write my background thermodynamics. No. Write parameters. Yes, I want to see how the parameters are being written. And write warning. No, do not write warning. And there is an input verb was just 1, because I don't want to see what are the inputs, many things, but I want to see what is the background verbose. Background means it will actually give you all these things that what are being calculated and so on. So it will by default it is 1. I have made it 3. Right, and also you can use the override route. Override is equal to y, because it will not generate different files for every run. It will simply use the same name and it will write again and again. So I hope this is already done. You see, they successfully installed the classy 3.3.4. Okay, now in order to run the program, what you have to just do that after you have already installed it, you have to write /class, and then we have to explain which file you want to run. I'm going to run explanatory.ini, right? So once I have done it, it will simply give me the output of what we have, right? So it is already taking care of age is calculating 14.4, NF is 3.04, conformal age is this one, the decimal required is this one is this one, baryon density is 0.04, omega density is this guy, and photon density is this one. Ultra relativistic species, we have this guy. Cosmological constant, although we don't have, because in order to make it equal, if you have not given you the correct parameter, it will try to give you omega cosmological constant, right? It is not of a problem. Again, dark energy fluid is 0.7 and omega is 0.334, and total baryon density is maybe this is omega h square, maybe, I guess, and there is a radiation, right? So total is omega 1, and over here omega is 0.4761. all right, so computing the thermodynamical parameter over here, and also it is computing the sigma 8. Sigma 8 is equal to 0.883414, and the it is actually trying to find out the spectrum up to certain k is equal to 4.68 h over megaparsec. All right, so this is the way we can also change the explanatory file, and we can make it like, okay, go to CLP, I don't want my bell, I will also write /class explanatory.ed, and it will also compute everything. So if you have doubt in my model, then you can see that 100 into theta star is equal to 0.9956. Sigma 8 is more or less 0.95, because we are using the for CLP we are using the omega 0 minus 2. So maybe if I use minus 1.2, and it is 0.2 over here. Although I have using bell ZT and bell delta, it is not a problem, because I have already specified which one is to use, CLP. Now you see that 100 into theta star is 1.026, sigma 8 is 0.87, something like that. Co-moving sound horizon is 144, and another one is co-moving sound horizon, RS is 147. So it has to be always near about 145. It has to be always near about 147 or something. Right, optical, that it is computing. Also it is computing what is the cosmological constant, very less, omega 0, omega fluid is equal to 0.7, and all, and different things. Age is 14 point something, and effective is 3.044, and so on. So in this way you can easily compute whatever you want. If I just given fluid equation nothing, right, and I have also just given omega fluid is equal to 0, then you see it will not show any error. It will simply computing omega constant, cosmological constant is 0.706, age is 13 point something, and effective is 3.046, sigma 8 is 0.8258, right, theta star is 1.046, and so on. Sound horizon is 144, and sound horizon over here RS is 147, right? So this is the way we can easily modify the background of class. We can run the code, and so on. In the next time, I'm going to talk about the many technicalities that is coming in the class, how we can change the perturbation scheme, because what we have talked about today is just the background part, and where you have to change. In the next video, I'm going to talk about the much detailed about technicalities of the class, and how you can change your perturbation quantities. Okay, so if you have liked this video, please comment and share to your friends. This is Tamil Nadu Cab signing out.